whispering, remember that feeling, looking up at the night sky. Last time we touched on Aryabhata's incredible idea, mapping that vastness with numbers, with geometry.
That framework he built.
Yeah, and this idea of the Khagola, our own personal view of the cosmos, and that physical model, the Gola Yantra.
A way to make it tangible.
Soaring, warm tone. Welcome back to the deep dive into the sources. So last time we set the stage right. Aryabhata's spherical universe, the observer's local sky.
The foundations, yeah.
Now we're going deeper. We want to see how Aryabhata actually provided a system, a practical way to measure things, calculate positions within that framework.
Getting into the real mechanics of it.
Exactly, the nitty-gritty of ancient astronomical measurement. And believe me, there are some surprising insights here.
It's more sophisticated than many might think.
Welcoming bright tone. Hello again, fellow explorer. It's kind of amazing to think, isn't it? Moving from this big abstract sphere.
To the actual problems someone faced, say, in Pataliputra.
Right. Looking up, trying to make sense of it all. Today, we're really digging into the geometry of that local sky, the Khagola, as Aryabhata lays it out in the Golapāda.
Okay, so where does he start?
He starts with the most obvious thing, really. The horizon. That circle around you where the sky seems to meet the earth.
The fundamental dividing line, up from down.
Exactly. It's our baseline. It sounds simple, but it's the anchor for everything else in your local view.
And it's completely personal, tied to wherever you happen to be standing.
Absolutely. Now, from that horizon, Aryabhata has us pinpoint the cardinal directions. North, Ūrdhvam; south, Yamya;
East, Prague, where things rise.
and west, Paschimodam, where they set. These aren't just abstract points, they're fixed markers on your horizon.
Anchors for setting up the rest of the local grid, you could say.
And we look up, straight up. That point is the Zenith, Ūrdhvam,
And directly beneath your feet, through the earth.
is the Nadir, Adhas. So you have these poles for your local system, top and bottom.
Right, defining the vertical dimension relative to the horizon.
And these points, Zenith and Nadir, help define vertical circles. Imagine slicing the sky vertically.
Like hoops passing through the top and bottom points.
And the most important one, unique to you, is the Meridian, the Dakṣiṇottarāśāstham.
Okay, break that down.
It's a great circle that runs from the north point on your horizon, straight up through the zenith,
Directly overhead.
down to the south point on your horizon, and then loops back under through the nadir. It's your personal north-south line across the sky.
And crucially, that's the line where celestial objects reach their highest point for the day, right?
Exactly. That moment of crossing the meridian culmination
Yeah.
or transit, that's its peak altitude. Super important for observation.
Okay, makes sense. Any other key circles?
Yes. There's also the prime vertical, the Samamaṇḍalam. Think of another vertical slice.
Huh?
But this one goes east, zenith, west. So from the east point on the horizon, up through the zenith, down to the west point.
Perpendicular to the meridian, then.
Exactly, at a perfect right angle.
So the horizon, the meridian, the prime vertical, they sort of carve up your local sky, don't they?
They do, into four main quadrants, essentially. And this framework lets us describe where something is using two coordinates.
Altitude and azimuth.
Precisely. Altitude is just how high it is above the horizon. Azimuth is its direction along the horizon, like north, northeast, east, etc., usually measured as an angle.
So that's the immediate observable system. What you see is what you measure relative to yourself.
Right, but here's the thing. The stars and planets don't actually move along those simple altitude-azimuth paths.
No, their daily motion is because the Earth is spinning.
Exactly. Their apparent paths are actually circles parallel to the celestial equator.
Yeah.
Aryabhata calls these declination circles Apakramamaṇḍalam.
Ah, so now we're connecting the local view to the bigger cosmic picture.
We are. Think of Earth's equator projected out onto the sky that's the celestial equator. And the daily paths mirror that.
And because Earth is tilted, these paths usually look tilted from our local perspective on the ground.
Unless you're right at the poles or the equator. Yeah. And this brings us to a really key universal coordinate. Declination. Apakrama.
Okay, so what's declination?
Aryabhata defines it formally. It's basically the celestial version of latitude on Earth. It tells you how far north, Ūrdhvam, or south, something is, from the celestial equator.
Measured in degrees, just like latitude.
Right. And the crucial point here is that declination is universal.
Meaning it doesn't change based on where you are or what time it is.
Exactly. Unlike altitude and azimuth, which are constantly changing for an observer, a star's declination is pretty much fixed. It's part of that stable grid on the celestial sphere itself, the equatorial coordinate system.
Like a permanent address in the sky.
That's a great way to put it.
Ah.
Now, Aryabhata also introduces another concept, maybe a bit more abstract, called the Unmaṇḍala.
The Unmaṇḍala. Okay.
It's defined as a great circle passing through the east and west points on your horizon, but also through the celestial poles, the points where Earth's rotation axis points in space.
East, west, and the poles. Sometimes called the 6 o'clock line.
Yeah, or the Equatorial Horizon, because things on the celestial equator would rise around 6 a.m. and set around 6 p.m., spending half their time above the horizon, defined by this Unmaṇḍala circle.
Okay, so how does this Unmaṇḍala relate to our actual horizon, the one we see?
Ah, that's the key. The angle between the Unmaṇḍala and your local horizon depends entirely on your latitude.
Right, because your horizon tilts relative to the celestial equator depending on how far north or south you are.
Exactly. And this angle is directly linked to why days and nights have different lengths throughout the year, what Aryabhata calls Kṣitijyā.
The waxing and waning of daylight. So how does the Unmaṇḍala explain that?
Well, remember the daily paths, the declination circles, are parallel to the celestial equator. The Unmaṇḍala acts like a reference. The angle it makes with your horizon determines how much of a particular declination circle is actually above your horizon. So if you're in the northern hemisphere in summer, the sun has a northerly declination. Because of the tilt between your horizon and the Unmaṇḍala, a larger portion of the sun's daily path stays above your horizon.
Longer daylight hours.
Right. And in winter, the sun's declination is southerly, so less of its path is above your horizon.
Shorter days. Got it. So the Unmaṇḍala is like a geometric tool for understanding that seasonal variation.
Precisely. It connects latitude, declination, and the observable length of day. Now, to help visualize all this, this spinning, intercepting geometry, Aryabhata talks about the Gola Yantra.
The physical model, the armillary sphere.
Yes. He specifies it should be perfectly round, samafad, uniformly dense, samaguru.
Also light, lagu, made of wood.
Right. It's meant to be a working model, not just decorative. A mini cosmos you can manipulate.
And it had to rotate smoothly, mimicking the heavens. He mentions methods for that.
He does, using mercury or oil or water, partalajala, basically to reduce friction at the pivot points.
Clever. Using liquids as bearings, essentially.
Yeah. And he stresses it needs skillful handling, swadhyā, and careful synchronization, with the actual sky's rotation about 1 turn per day.
So it really was an instrument, not just a visual aid, like an analog computer.
That's a perfect description. An ancient analog computer for spherical astronomy. It lets you see how these circles, horizon, equator, ecliptic, intersect from different viewpoints, makes the abstract geometry concrete.
Which must have been incredibly helpful for teaching and for, well, wrapping your own head around it.
Absolutely. So with this model established both mentally and maybe physically,
Aryabhata moves towards calculation.
Exactly, applying math and observation. He introduces a concept called Kṣitijyā.
Kṣitijyā, Sine of the Ascensional Difference. Okay.
And this ties directly back to that variation in daylight, the Kṣitijyā, and the role of the Unmaṇḍala.
So what is ascensional difference exactly?
It's basically the time difference. How much earlier or later does something rise compared to if it were right on the celestial equator? That difference depends on its declination.
Okay, so Kṣitijyā is a measure related to that time difference.
It's the sine of the angle corresponding to that time difference. And Aryabhata gives us the formula.
Ah, the math bit. Let's hear it.
It's calculated as arsin.
Okay, let's break that down. R is Aryabhata's standard radius, 438 minutes of arc.
Right. Delta, that's the declination of the object, its north-south position.
And phi, that must be the observer's latitude on Earth.
Correct. So the sine of declination times the sine of latitude divided by the cosine of latitude, all scaled by r.
Okay. So what does the result, the Kṣitijyā value, actually tell you? Forget the trigonometry for a second.
Practically. It tells you how much sunrise or sunset for that object at your latitude deviates from the sort of ideal 6 p.m. times relative to solar noon.
Ah, so it quantifies the earliness or lateness of rising and setting caused by declination and latitude.
Exactly. A positive Kṣitijyā means it rises earlier and sets later than something on the equator. Negative means later rise, earlier set.
So this is the mathematical key to actually calculating the length of any given day or night at any latitude based on the sun's declination for that day.
Precisely. It connects the geometry directly to observable time spans. A huge step for predictive astronomy.
Really moving beyond just mapping to forecasting.
Yeah. And building on this, Aryabhata then discusses Cara, the unequal rising times of the zodiac signs.
Okay, Cara, what's the issue here?
Well, if you're on the equator, the celestial equator rises vertically. All the zodiac signs, which lie along the ecliptic,
The sun's path.
they take roughly the same amount of time to rise above the horizon. About 2 nakhas, he says, equal time segments.
But that changes if you're not on the equator.
Drastically, because the ecliptic is tilted relative to the celestial equator, and your horizon is tilted relative to that. The angle at which different parts of the ecliptic rise changes.
Ah, so some signs rise at a steeper angle to the horizon and some rise at a shallower angle.
Exactly. Steeper angle means it takes less time for the whole sign to clear the horizon. Shallower angle, it takes longer.
Unequal rising times, Cara.
That's it. And how do we calculate this difference?
Let me guess. Kṣitijyā comes back into play.
You got it. The Kṣitijyā calculation gives us a correction factor. It's called Caradala. Literally half the Cara difference.
Okay, so you calculate this Caradala based on the sign's general declination and your latitude.
And then you take the standard equatorial rising time Divāsapada, a quarter of a day, and you either add or subtract this Caradala correction.
Depending on whether the sign is north or south and your latitude.
Right. And that gives you the actual time it takes for that specific zodiac sign to rise at your location.
That's pretty sophisticated. And important for things like astrology, I imagine, determining the ascendant.
Hugely important. The ascendant, or Lanya, is the sign rising on the eastern horizon at a specific moment, like birth. Calculating it accurately requires knowing these unequal rising times.
So it had very practical applications within their worldview.
Definitely. So let's recap this dive. We've really gotten into the weeds of Aryabhata's system, mapping the local sky horizon, meridian, prime vertical.
Connecting that local view to the universal coordinates like declination, using concepts like the Unmaṇḍala.
Understanding the Gola Yantra as this amazing analog computer, a physical tool.
And then starting on the practical calculations using Kṣitijyā to figure out daylight length.
And using Cara to understand the unequal rising times of zodiac signs.
It's a clear progression, isn't it? From the big concept of a spherical cosmos down to the mathematical tools needed to actually measure and predict things from right where you stand.
It really is. He's building a complete system, moving from theory to practical application.
From philosophy to applied science, in a way.
So, thinking about all this, the detailed models, the complex math for their time, it makes you wonder, doesn't it, what were the really crucial day-to-day applications for people back then?
Beyond the purely astronomical or astrological, you mean?
Yeah. How did this knowledge filter down? Did it impact timekeeping, calendars, maybe navigation, agriculture? How did understanding your local sky and its rhythms actually shape life in ancient India?
That's a great question. The practical impact beyond the specialized calculations.
Something to think about. Now, next time, we're going to continue digging into these practical calculations in the Golapāda.
More applications of the geometry and math.
Yes. We'll look at how they used shadows, just the shadow of a vertical stick, a gnomon, to figure out their latitude, how they calculated altitude from position.
And we get into parallax too, right? That
Yeah.
slight shift in viewing position.
Exactly. Parallax becomes really important later on. So plenty more fascinating details to uncover. We hope you'll join us for that.